Bismillahirrahmanirrahim. Assalamu alaikum, students. Last time we discussed the mathematical properties of state functions. So today we will continue with that topic. So I write the mathematical properties of state functions. So I write here continued. What we said, we considered 1 mole of an ideal gas. So we said for an ideal gas, PV is nRT. Now N is 1 mole. We can write P as RT by V, right? So we said this can be written as function of volume and temperature. Then we evaluated partial derivatives and we wrote this equation dP is equal to P by T at constant V dt plus P by V at constant T dV. I named it now equation first. You can connect this lecture to previous lecture. I am naming this equation first in this particular lecture. So we said change in pressure, differential change in pressure, that means a small change in pressure in an ideal gas can be written this way using this equation first. What is dou P by dou T? It is the partial derivative of pressure with respect to temperature, keeping volume constant. dt is differential change in temperature plus partial derivative of pressure with respect to volume, keeping temperature constant, and dV is the differential change in volume. So from this equation first we can find differential change in pressure in an ideal gas. But remember, we said that this is valid only for small changes in pressure. Why so? Because over large change in pressure, these partial derivatives may change. And if they change, we have to take their change into consideration as well and consider second order derivatives also. When changes are small, these partial derivatives over that change are assumed to be constant, right? Then we talked of mixed second order derivatives. We said for an state function, the order of differentiation doesn't affect the outcome. What we did, we found first derivative of pressure with respect to volume, keeping temperature constant. Then we differentiated the result with respect to temperature, keeping volume constant. We got minus R by V square as our outcome for this ideal gas. Then we did the reverse. We first differentiated pressure with respect to temperature partially, keeping volume fixed. Then the result was differentiated with respect to volume, keeping temperature fixed. We got same outcome, minus R by V square. Then we said it is not just for pressure, which we took as an example. In this case, this is a general property of any state function, that mixed second order derivatives are equal, right? And we said this can be used as a test for a function to check whether it is a state function or not. Then second thing was we said if I have some function z of xy which can be rearranged to give x equal to g of yz or y equal to h of xz, can be rearranged to x is equal to g of yz or y equal to h of xz. Then we have these two properties. We can write dou x by dou y, keeping z constant, as reciprocal of dou y by dou x, keeping z constant, right? I name it second in this lecture. And also we said there is a cyclic rule. What is cyclic rule? Cyclic rule says dou x by dou y, z constant, times dou y by dou z, x constant, times dou z by dou x, y constant. This product is equal to -1. I name it 3, right? This is valid for such kind of function, right? And we said in case of pressure, we have this case. We can write P equal to nRT by V. So you can write pressure as function of temperature and volume. Then you can write volume as nRT by P, and you can write T equal to PV by nR, right? You can write P equal to nRT by V, V equal to nRT by P, and T equal to PV by nR. That means you have this kind of function here, that pressure is a function of temperature and volume. So you can rearrange the things and make volume as function of temperature and pressure, and temperature as function of pressure and volume. So cyclic rule can be applied here. So what we do now, we can rewrite our equation first by making use of second and third. So I write, this is my first, I write we reformulate equation first by using equations second and third, right? First step, this one. I reformulate this using these two rules. What I get? See what we get. So we can write dou P by dou V at constant T times dou V by dou T at constant P times dou T by dou P at constant V equal -1. We have made use of cyclic rule. So dou P by dou V at constant T times dou V by dou T at constant P times dou T by dou P at constant V is -1. So it is simple. PVT, P corresponds to X, V corresponds to Y, and T corresponds to Z. C, X, Y, Z. So here you have PVT, then you have YZX, YZX, here you have VTP, then you have ZXY, you have TP, V, right? Now, let me use this color. I can write dou P by dou T at constant V equal to minus dou P by dou V at constant T times dou V by dou T at constant P. See what we have done? I have written dou P by dou T at constant V equal to minus times dou P by dou V at constant T times dou V by dou T at constant P. See how? It is dou P by dou V at constant T. So this is same as this. And this is dou V by dou T at constant T. So it is same as this. Now look at this right hand side. If I take this downstairs, this will become here -1 by dou T by dou P and V. Dou T by dou T at constant V. Then I use this reciprocal rule. So I can write that reciprocal equal to dou P by dou T at V, and minus will remain. Got it? So I'm saying this, I shift to right hand side, it will be downstairs, then I make use of the reciprocal rule, 1 by -1 by dou T by dou P at constant V will be written as minus times dou P by dou T at constant V. So I get this expression. To think about it, it is easy. Think about it. What I do, I write it equal to minus dou V by dou T at constant P over dou V by dou P at constant T. What I do, I write it dou V by dou T at constant P. So this I have kept as it is. Then I have written it, converted into reciprocal. When I reciprocal it, I write it dou V by dou P at constant T. Got it? So this factor I have converted into reciprocal, dou V by dou P at constant T. So I have now minus dou V by dou T at constant P over dou V by dou P at constant T. Then what we do, we write it equal to beta by K. What is beta and what is K? K, you know, K is isothermal compressibility, where K is isothermal compressibility. Isothermal compressibility. And beta is volumetric thermal expansion coefficient. A is isothermal compressibility and beta is called volumetric thermal expansion coefficient. Now, K is minus 1 over V dou V by dou P at constant T minus 1 over V dou V by dou P at T. This we have already discussed. It is simply, this compressibility is simply reciprocal of bulk modulus. Remember the definition of bulk modulus, which is change in pressure per fractional change in volume. So it is reciprocal of that. You have fractional change in volume in the numerator and change in pressure in the denominator. But since you are keeping temperature constant, so we call it isothermal compressibility. So it is simply reciprocal of bulk modulus, which we have already discussed, but it is isothermal compressibility. So we are fixing the temperature during change in pressure, right? Now, what is volumetric thermal expansion coefficient? It is by definition 1 over V dou V by dou T at P. This you know from your previous classes, but I refresh it. It comes from thermal expansion. Let me make that clear first. So I go to thermal expansion. thermal expansion, we know when the temperature of a body increases, it usually expands. One exception to this is water between 0 degree and 4 degrees Celsius, which contracts when the temperature increases. In this temperature range, 0 and 4 degrees Celsius. Now, in thermal expansion, we define different coefficients, like we define coefficient of thermal expansion, alpha, you might know. We define coefficient of area expansion, beta, or I should write some other symbol. Coefficient of area expansion, we write, let me call that gamma. And we define coefficient of volume expansion, which is our beta. How we define that? We define beta this way in thermodynamics. Limit delta T tending to 0, delta V by V naught over delta T. At constant pressure, right? So idea is we define, it is also called expansivity. Expansivity. Expansivity or coefficient of volume expansion or volumetric thermal expansion coefficient. So what is the idea? Idea is if we have some substance and we change its temperature by delta T amount, if its original volume is V naught, its volume will change by amount delta V, then this ratio of fractional change in volume to change in temperature, as temperature change approaches 0, this thing is called beta. You can see it will have SI unit of per Kelvin. Numerator is unitless, but during this change in temperature, when an object or substance is subjected to this change in temperature, it is assumed that its pressure is kept constant. So this is same. See, there is fractional change in volume per change in temperature, so pressure is staying constant. So it is simply expansivity or volumetric thermal expansion coefficient, right? So let us move back to our topic. So we said it is beta by, it is now beta by K. It is moved to this. I said this can be written as beta by K. What is it? It is dou P by dou T at V. It is beta by K. How? You see, you check it. If you divide this beta by this K, this 1 over V will cancel, and you will get minus dou V by dou T at constant P over dou V by dou P at constant T, which is same. Dou V by dou T at constant P, which is this. And in denominator, you have dou V by dou P at constant T. So it is beta by K. Now, I can write then dou P by dou T at constant. It was dou P by dou T at constant T. Let me name this equation. It is my dou P by dou T at constant V. Let me name this. This is my 4. This was 3. This is my 4, dou P by dou T at constant. Sorry, it is dou P by, okay, it is dou P by dou T at constant V. It's okay. So it is this partial derivative in equation first. See, in equation first, we have two partial derivatives. One is this, one is this. Or one is dou P by dou T at constant V, which we have showed to be equal to beta by K. Now we have another partial derivative, which is dou P by dou V at constant T. I write directly, but when you check it, I write here, one more, skip it a page. So I write similarly, dou P by dou V at constant T is equal to minus 1 by K into V. I name it 5. This is my 5, and I write chuck it at home. So I am claiming that similarly dou P by dou V at constant T is minus 1 by K V, where K is what? It is isothermal compressibility. So we have found the second partial derivative dou P by dou V at constant T in equation first. This is my equation first. Dou P by dou V at constant T we have obtained. So I can substitute the values of these partial derivatives in first, that is 4 and 5. So I write using equations 4 and 5 in first, we get, that means putting the values of these two partial derivatives, this one and the one in equation 5, this one in equation 1. This is my equation 1. I write the change in pressure is beta by K dt minus 1 by Kv dV. So I name it 6. Beta by K dt minus 1 by Kv dV, right? So we have substituted the values of partial derivatives, right? Now I have to mention one thing. See, beta and K, that is volumetric thermal expansion coefficient and isothermal compressibility, can be evaluated for any real substance like some nitrogen gas. And the partial derivatives, these partial derivatives are abstract mathematical quantities, dou P by dou T at V, and this one, dou P by dou V at constant T. But you see how equations 4 and 5 connect these abstract mathematical quantities with the two experimentally measurable physical quantities, beta and K, right? Now, if you have to now find the finite change in pressure in some gas, as we said, or some substance, you can integrate this equation. So I can write Ti to Tf beta by K dt minus Vi to Vf 1 over Kv dV. We have integrated 6 to get some change in pressure if the system changes from initial state having temperature Ti and volume Vi. If, for example, some gas changes from state I to F, Ti, Vi being the temperature and volume in its initial state, Tf, Vf being the temperature and volume its final state. So we can get the change in pressure as the state changes by this integration, right? We can further simplify it. We can write it beta by K. Since temperature is state function, it is simply Tf by Tf minus Ti. Then you have minus 1 over K outside, and the integration will give you the natural logarithm of Vf by Vi. And in equation 7, I encircle it. Right? We obtained a beautiful equation. And I must mention here that this equation second holds if delta T and delta V are small enough that beta and K are constant over the range of integration, right? They are valid only when the change in pressure and change in volume are small enough that beta and K are constant over the range of integration. Now we collectively do a sample problem. I write sample problem. Part A. It says calculate what? Dou F by dou X, Y constant, dou F by dou Y, X constant, then dou 2F by dou X2, Y constant, then dou 2F by dou Y2, X constant, then what? Then dou F by dou X, Y constant, we differentiate that with respect to Y, treating X constant. And dou F by dou Y, X constant, we differentiate that with respect to X, treating Y constant for the function f of xy is equal to y e raised by x plus xy plus x natural log of y. See, I repeat what we have to find. Question says, it's part A. Calculate dou f by dou x, y constant, dou f by dou y, x constant, dou 2f by dou x to y constant, dou 2f by dou y to x constant, then dou f by dou x, y constant is to be differentiated with respect to y, treating x constant, and dou f by dou y, x constant is to be differentiated with respect to x, holding y constant, right? And function is y e raised by x plus xy plus x ln y. Then part B of the question says, part B, it says determine if fxy, the given function, is a state function of the variables x and y. Part B is saying determine if the given function is a state function of the variables x and y. We know the test of mixed second order derivatives. If they are equal, that means these two derivatives. See, in this we are first differentiating with respect to x, treating y constant. Then we are differentiating the result with respect to y, treating x constant. In this we are doing the reverse. First we are differentiating the function with respect to y, then with respect to x. So if this derivative and this derivative are equal, then function is a state function. That is what we have discussed. Part C says if fxy is a state function of the variables x and y, what is the total differential df? If fxy is a state function of the variables x and y, what is the total differential df? Right? Now we move to the solution. Let me use some other color. Use this below. Solution for part A first. So first I find dou f by dou x treating y constant. What we get, y is constant. This is my function. First term I will get e raised by x. Second I will get just x. We are differentiating with respect to x. So y is constant. Here you will get y times e raised by x plus derivative of e raised by x is e raised by x. Y is constant. Here we will get just y. The dou by dou x of x is 1. Here we will get x is constant. Sorry, y is constant. We get just ln y. I write my answer is dou f by dou x with respect to y is y e raised by x plus y is elementary differentiation plus ln y. It is dou f by dou x, y constant, y raised for x plus y plus ln y. Then I do dou f by dou y x constant, which is e raised by x plus x plus x by y. Differentiating here the function with respect to y partially treating x constant. So you will get this. You can check here y is constant, so it will remain as a sorry, here x is constant. We are differentiating with respect to y, so e raised by x will remain. It will dou y by dou y is 1. We are differentiating with respect to y now. Differentiating with respect to y, only x will remain. Differentiating with respect to y, what we get, x will remain as constant and ln y will, differentiation of ln y will be 1 over y. And x times 1 over y, right? Then we find second order derivative, dou f, dou 2 f by dou x2 treating y constant. What does that mean? It is dou 2 f by dou x2 treating y constant. So I have to differentiate this once more with respect to x. What you get? When you differentiate this with respect to x, first order derivative treating y constant, these two terms will be 0. They contain only y. It will be y constant. Differentiation of e raised by x is just e raised by x. It is dou 2 f by dou x2 y constant. Now I find dou 2 f by dou y2 x constant. Means another color. Dou 2 f by dou y2 x constant means I have to differentiate it once more with respect to y, treating x constant. X is constant, first two terms are 0. So you have to differentiate, then third term, x is constant, and 1 by y will have differentiation of minus 1 by y square. So either just minus x by y square. Dou 2 f by dou y2 x constant is minus x by y square. Then move to next. Then I have to differentiate dou f by dou x treating y constant with y treating x constant, right? So what I have to do, I have dou f by dou x, that means partial derivative of function with respect to x treating y constant. You have to differentiate with respect to y treating x constant. That means this is my dou f by dou x with respect, and dou f by dou x treating y constant. I have to differentiate it with respect to y treating x constant, right? When I do that, y constant, this will be 0. This is also 0. What I get is simple, the differentiation of first, sorry, it will, first I will write the answer, I will check it. So 0 is yx plus 1 over y. See what I have to do, I have differentiation and derivative of function with respect to x. I have to differentiate it with respect to y, right? So my first term is y raised by x. I'm differentiating with respect to y Dou y by dou y is 1. E raised by x will remain in first term. Then dou y by dou y is 1. In third term, which is ln y, differentiation of ln y with respect to y is 1 over y, right? Then what I have to do, I have dou f by dou y, treating x constant. I have to differentiate that with respect to x now, treating y constant. I have dou f by dou y with respect to x held constant. It is to be differentiated with respect to x, treating y constant. It will be e raised by x plus 1 over y. We check it. So you have to differentiate this with respect to x now. With respect to x now. So first term e raised by x, e raised by x. This will be 1 with respect to x, and third term will be 1 over y. So you can check these mixed second order derivatives are equal. That means order of differentiating the given function with respect to x and y is not affecting our outcome. We get the same result. So we got the answer for part B, because we have shown that dou f by dou x with respect to y differentiated with respect to y, treating x constant the same as differentiating function with respect to y first, keeping x constant, then differentiating the result with respect to x, treating y constant. We have shown that these mixed derivatives are equal. I check it first. Dou by dou y x constant, dou by dou x of y. Therefore, right, since they are equal, therefore f xy is a state function of the variables x and y. Let us move to part C. Part C. Where to find the total differential? The total differential is given by df is dou f by dou x y constant times dx plus dou f by dou y x constant times dy. Dou f df is dou f by dou x y constant times dx plus dou f by dou y x constant dy. Then we substitute simply the partial derivatives which we have obtained, which is first y e raised by x plus y plus ln y times dx plus e raised by x plus x plus x by y dy, y e raised by x plus y plus ln y dx, then plus e raised by x plus x by y dy. So these are simply the derivatives with respect to x and with respect why, right? So we have done this question. This way you can do other questions. So this is all for today. Do your homework, and whenever it is given to you in the video lectures, follow all the lectures, make notes out of these lectures, make your notebook, learn at your own pace from these video lectures, and do not forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.